All right, set 2, 2024 AP Physics C E&M questions. Last set. I'm getting a little bit tired after doing the fourth set here. This is, you guys are troopers for doing both mechanics and E&M tests. Like, I know I'm doing sets of FRQs, but you guys had to do the multiple choice. So, this is a draining process here. Anyway, if I have any corrections, I will put it in the pinned comment in the video. Non-conductive rod of uniform negative linear charge density is near. So there's a negative charge. Okay, I gotta confuse myself because the previous says a little bit different. With a positive charge here, the rod held at rest, equipotential lines, blah, 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 adjacent marks. Okay, calculate the absolute value of the electric flux through this surface here. So electric flux is here, but luckily with Gauss's law, it's just enclosed charge over epsilon naught. I noticed you guys don't look like you got an easy Gauss's law question like, you traditionally get. So the enclosed charge is the sphere, which is 1 nanocoulomb. And the epsilon naught is 8.85 times 10 to the negative 12. So this will be 1e negative 9. It's a positive charge, right? It's positive 1 nanocoulomb. Yes, okay. 8.85 e minus 12. And that is 113... what is this? I forgot. Newtons per coulomb times meter squared. I don't know. I've never do like flux units. Right? That's like weird. Doesn't mean any. Or it's like the units not something we commonly deal with. Okay. Positive test charge is held at point C. External force is applied, and we go from C to E to D to A. Test charge is momently held at rest. The bar shows the absolute value of the work done by from C to E. So the work is just going to be Q times the change in potential. It's going to be proportional to the potential difference here. So from C to E, so let's look at where we are. From C to E, the potential difference is 20 volts, right? So that's kind of the baseline. That's 20. Now from E to D, well, this is the same potential, right? So there's no work done. So this is going to be 0 here. And then from D to A, that potential difference is, it looks like A is 10, right? So from 0 to 10, that's a 10 volt potential difference. If this was 20, so we're going to do exactly half here, half, right? Or, oops, I don't have to draw the full bar. I just draw like a little, now I'm just being picky, but just do a half bar like there, like that. Okay, because this was 20 volt difference, this is a 10 volt difference, half of that. Calculate the approximate magnitude of the x component of the electric field. So the magnitude of the electric field is going to be approximately the change in, it's the derivative, right? But we're just going to approximate it. So if we're at position B, where's B here? Okay, so you have to think about over this whole region, you can think about like, well, I'm going from negative 20 to negative 10. So this region, the potential difference is negative 10 volts. Or 10 volt difference. And then how many hash marks is it? It's about, let's see, 1, 2, 3, 3.5 of these hash marks. So 3.5 times 0.4. That's probably what I would use for an estimate. 1, 2, 3. I don't know. I'm probably a little bit less than 3.5, but whatever. 3.5, close enough. So I would say it is 10. And because it's magnitude, it doesn't matter if it's positive or negative. 3.5 times 0.4. So I'm going to say 10 divided by 3.5 divided by 0.4, and that is 7.14 newtons per coulomb. Okay, positive test charge placed at position C. It's a positive test charge, and then what's the direction of the net electric force? Okay, so point C. Okay, now remember the electric potential lines, the electric field lines are perpendicular, so it's going to be kind of a vertical thing. So it's perpendicular at this point. Now the question is up or down. Well, electric field's always going to point from higher potential to lower potential. So this is negative 10, this is negative 20. So lower potential is going to be going that way. So the electric field's going to point downward. And remember the rule for the electric field, or if I put a positive test charge, it's going to move a force in the direction of the electric field. So this is going to be negative y direction here. Negative y direction. And that's because the E field is perpendicular to equipotential lines. Is perpendicular equipotential lines and points from higher to lower potential, which is downward, which is negative y direction. And then the last is a positive charge would feel a force in the same direction as the E field. If it was a negative charge, it would be opposite direction of the E field. Okay. All right, sphere and test charge are removed. Rod is a length 2L, uniform negative linear charge density. The rod is held at rest on the y-axis, and we want to find the electric potential for Vp at some location yp greater than 2L. So this is like yp. All right. So actually very similar. Your set 1 and set 2s are pretty close in structure. So how do we handle potential? Well, the only formula we have for potential is you could do the electric field and then take the derivative. That's one way. But there's a more direct way. It's kq over r. Now this is for a point charge, and we don't have a point charge. We have a rod of charge. So what you do is, to make point charges, you chop this up into a tiny charge, right? This is going to be dy. And then the charge, the amount of charge dq on there is going to be negative lambda dy. Okay? Well, actually, yeah, negative lambda dy. For potential, we do use the sign of the charge because that is important to have positive or negative potential. So then we say the potential contribution from this guy is k dq over r. So just the little bit of charge there. That's k. This is negative lambda dy. And then what is r? Well, the distance, this distance from here to here is y. Okay, that's the location of this point charge. So the distance from here to here is yp minus y. And you want to use a positive value of r. So it's going to be the top y value minus the larger y value minus the smaller y value. So that's going to be yp minus y. Okay, and we can distribute that negative sign and flip this around. So it'll be k lambda dy over y minus yp. That's going to be dv, and then we're going to integrate it. We want to add it. The integral is just now adding, because I said, well, this is the potential due to this guy, and then I want to add them all up from 0 to 2L. Okay, so then that's going to give me k lambda, and this is natural log y minus yp from 0 to 2L. That's going to be k lambda, natural log of 2L minus yp, minus k lambda, natural log of 2L minus 0. And then you can factor out the k lambda, and then do the natural log, and then combine these natural logs by dividing them. 2L minus yp over 2L. Oh, but they want a negative sign. So they're going to pull out a negative sign and then, flip it upside down, which is valid. If you want to make it look at the same. So you have to factor out a negative 1, then this one's positive, this one's negative. K lambda ln 2L over 2L minus yp. Okay, cool. So it matches, wait. Oh, this is not 2, I don't know why I said this is 2L. This is 0 minus yp. This is just minus yp. Yeah. So this would be minus yp. But you can multiply the top and bottom by negative 1. So negative k lambda ln yp over yp minus 2L. Okay, cool. Finally. Okay, figure sketch the graph of the y component of the electric field. So the EY is just going to be negative dv dy, okay, of this part here. And so our potential is really negative k lambda ln, and instead of yp, just call it y over y minus 2L. Now, I think this is easier to do the derivative if you, just separate this ln of y, not combining it into a single fraction. So this is negative k lambda ln of y. When I take the derivative of this now, is going to be 1 over y minus 1 over y minus 2L. Now, y minus 2L, this is actually smaller than this thing, right? Because it's a smaller denominator. So this whole thing is bigger. So it's more negative. This negative would make that, if you distribute the negative, you get k lambda 1 over y minus 2L minus 1 over y. That's actually going to be positive. So the electric field should be positive. Is that correct? What's a negative charge? So ought to point towards it. So why do I have the term correct? Y over y minus 2L. Oops, sorry. Y over y minus 2L. 1 over y. This is, if I plugged in like 10, this is bigger. Why did that happen? Must have messed up something somewhere. Oh, there's a negative sign here. Psh, I forgot that. So that negative cancel with that negative. It makes this positive, right? And so this is negative. Okay, yeah, so the whole quantity is negative. Okay, cool. I caught where my issue is. So it is negative electric field. And I knew that because this is a negative charge, so the electric field ought to point downward towards the negative charge, right? Because if I put a positive charge here, right, it's going to be pulled towards that guy. All right, so now this kind of has a vertical asymptote right at negative 2L. So it's going to kind of do this, and then it's going to approach 0. It's kind of what's going to happen. Okay. All right, number 2, circuit question. Students, it's almost the exact same problem as set 1. It's just series resistance instead. Determine the resistance R of identical resistors RA, RB. The resistors are connected in series. Diagram that increases. So we want to, actually, when I measure quantity that increases. So what happens is when you first close it, initially the voltage is 0. Initially the current is 0. Because there wasn't any current before, and when I close the switch, there's still no current, right? So initially, these guys have 0 volts, and these guys have all of the voltage drop. And then over time, this will go to 0, and this will increase to epsilon. Because the loop rule says that like the sum of the total voltage drop has to be this guy, right? So so the inductor is going to go down, the resistor is going to go up. So we want to measure the voltage across the resistor here like this. This is what we want, okay? Because we want to know where the voltage is going to increase over time. Describe a procedure for collecting data that will allow students to graphically determine the experimental value of R using measured quantity that increases with time. So we're going to we're going to close the switch. I'm going to record the voltage as a function of time. Okay, I'm going to mark T 50% is when, you don't have to pick 50%. You can pick any time. When, I mean, honestly, like there's well, I'm not going to go to that rule. There's one rule that says like one time constant. You could record the time where it's one time constant away. One time constant, I think, is like 31% of the original voltage or something. It drops 69%. There's like a rule of thumb, but honestly, I'm just going to pick the 50% point because I think that's like the most straightforward to like is when the voltage equals 50% of epsilon. I think that's just easier. You could pick any percentage technically. Just pick some point and we use that. And then we'll repeat this 10 times. Okay. Or so I guess you would say you would by open the switch and wait for inductor to stop having a voltage or the inductor voltage to go to 0. You probably don't need to put that, but just to be explicit, you're gonna let it get back to its original state and try it again. Represents the expected trend, so label the quantity. So what's gonna happen here is inverses. So the voltage across the inductor is gonna do this. Okay. So, but the total voltage drop on the loop has to be this. So that what that means is the resistor voltage loop is gonna do this instead. So it's gonna look quite like this. And this is epsilon. And then we want to mark the 50% point. This is T 50%. This is epsilon over 2. Okay, and that's what we're going to record. Describe how the information graph used to determine the experimental value. Well, we know that the voltage, what's going to happen is the voltage across the resistors. Okay, so this is volt. I need to put volts. Sorry, V for volts. And then this is time in seconds. Label any appropriate intercepts, asymptotes, quantity. Yeah, okay. So the voltage here is going to be, the quantity is epsilon 1 minus e to the minus t over the time constant. Okay, so at time 0, it starts at epsilon. If you wait a long time, it's going to go to 0. So this is the equation for the resistor one. The other one's going to be just e to the minus t over tau, where tau is equal to L over R. So what we're going to do is we're going to say, well, when this over tau, the time constant, is equal to 0.5 epsilon, that's going to cancel, and that means e to the minus t over tau equals 0.5. And that means you take the natural log of both sides. Negative t over tau is equal to ln of 0.5. So the time constant, this is t 50%. T 50%, which is equal to L, so you want to solve for tau. Tau is going to be negative t 50% over ln 0.5. Yeah, and that's equal to L over R, R equivalent. R equivalent, by the way, is 2R, because they're in series, right? So it's technically 2R, which is L over 2R. And so I'm just deriving this part, L over 2R. So then the R is going to equal, move the R up and move that up. It's going to be L natural log of 0.5 divided by negative 2 t 50%. Okay, so describe the information of the graph part B. Which part from the graph would be used to determine the experimental value of R? So you would use that to calculate what R is from that information. Okay, I just want to check my algebra. I know that's something I mess up a lot, but I think I did that right. Okay, starting with the appropriate Kirchhoff's loop rule, derive but do not solve a differential equation that be used to determine I as a function of time. Okay, so you have a circuit here, and you just want to say the voltage across this resistor and the voltage across this inductor. You want to label these things, and then here's the current. And the way the loop rule works is you just say, like, well, this voltage is epsilon. And then we're going to drop IR, I times 2R, because they're in series. And then we're going to drop VL, but VL is equal to L di dt. L di dt equals 0. So that would be my differential equation. Has an I in it, has a di dt. That is the differential equation. Okay, so put that there. Move that over there. Okay, cool. After reaching steady state, the absolute value of the potential difference across RA is going to be delta V1. Okay. Oops. Let's see. And then the students replace the original inductor with a new inductor as a non-negligible resistance. The experiment is repeated. After a long time, the absolute value of the potential difference. Okay, so non-negligible resistance. The experiment is repeated. What's the potential difference? Okay, so in steady state, the way you want to think about it is you have this thing. The inductor is pretty much just ideal and shorted. So this is RA, this is RB, and then when you wait a long time, there's no voltage across the inductor. But if you include a little bit of resistance now, so if in the first scenario, this thing's going to experience half the voltage drop, right? Because there's the same resistance, they can have the same current going through them. So there's half the voltage drop here and none through here. Well, if you insert a little bit of a resistance there, now there's some voltage drop here. This is going to have to shrink a little bit, right? It's supposed to be smaller because in the original, with negligible resistance, the voltage drop across the RA was just equal to epsilon over 2. But if the inductor has some resistance, then some voltage drop occurs across it, and thus the total, and thus V RA has to be less than epsilon over 2, because the total has to add up to epsilon. So it's going to be whatever's left over divided by 2. Okay, cool. I'm running out of gas, but last FRQ, I think. Okay, cool. So wire connected resistance R form a rigid square loop of side length D. An external force is exerted on the loop, so the loop always moves with constant speed V in the X direction. The loop that enters region 1 of external uniform magnetic field of magnetic B that is directed in the positive Z direction. Region 1 has boundaries from D to 2D. The loop enters region 2 of external uniform magnetic field is 2B, directed in the positive Z direction. Region 2 has boundaries 2D and 3.5D. S is the leading point of the loop. So very well specified question, by the way. I like this style of question. Sketch a graph of the magnetic flux through the square loop as a function of position from S to 0.5D. Okay, so here, there's no flux entering it. All the way to D, when this gets to D, we have no flux entering it, right? So no flux, there's no magnetic field going through the loops from 0 to D. Then once this point passes D, now we're going to have some flux entering in here, right? It's going to increase linearly until we get to 2D. So it's going to go up, and we're going to increase it to some value at 2D. Okay, so now we've contained all of this flux, okay? We've contained all of that flux there, and now we're going to increase it again. Now, how much are we increasing it by? Well, it's almost like however much we increased over here, we increased by this much. So it's actually just going to continue on with the same slope all the way until we get to 3D. Because once we're in 3D, we're fully in here. So once we get to 3D, then we're fully in there, and then we've capped out. Right, until we enter 3.5D, and then it will start to decline, because then the leading edge, then the loop won't fully be in here. So once we get to 3.5D, then it will start to decline. And by the time we get to 4.5D, the loop will be entirely out. So we need to be 0 by the time. It would just have gotten out to a flux of 0. So we need to decline all the way to 0 at this point. Like that. All right, consider the instant when point S reaches 1.5D. So like right around here. 1.5D on this picture is going to be like, it's like halfway in, right? Indicate whether the current in the square loop is clockwise, counterclockwise, or 0. Okay, so the flux is increasing out of the page, right? So that means we have to induce a magnetic field into the page. Oops. Sorry, I'm having a hard time. Into the page. Okay, and then on the left side, in order for it to be induced into the page, it would have to go upwards like this, right? So then it's up, and it's going into the page from my perspective on that left edge. So it's going to be clockwise. And the justification for this is always going to be about Lenz's law. So there's increasing flux into the out of the page. And that implies we induce a B field into the page to counteract. That's Lenz's law. Thus, and then the right-hand rule, thus the I is clockwise. Okay, derive an expression for IS when point S reaches 1.5D. If IS is 0, indicate how the derived expression shows that IS is 0. Express your answer in terms of R. Okay. Derive an expression for IS when point S reaches 1.5D. Okay, so we just want to do the voltage is the derivative of the flux, right? And that's the derivative, well, of B times A. Now the magnetic field is constant, so it's just about the area. And the area, by expression, is going to be like, we call this X maybe. How much is that dimension times D? X times D, right? And then, sorry, times the derivative of x times d. D is constant. dx dt is the velocity, so it's vvd. So that's the voltage. And then the I is equal to v over r. So that's v times d divided by the resistance, like that. Okay, derive an expression for the power dissipated by the resistor when it reaches there. Well, if I have the current, well, you could do the voltage. You could do v squared over r, or you could do I squared R, or you could just do I times V. You do this times this. Any one of those will work, but here's the voltage, here's the current, so it's going to be V squared, D squared over R. All right, total energy dissipated by the resistor as it moves from 0 to 0.5 D is E original. The vertical boundary is now shifted to 2.5 D. After the boundary is shifted, the square loop again moves with V in the positive x direction shown in the figure 2. The total energy dissipated as it moves from 0 to 0.5 D is E new. Indicate whether E new is greater than, less than, or equal to E original. So all of the energy actually occurs when we are, changing the flux. So as we enter this region, the thing is we're not, I think it's going to be the same. Let me take a look at the original picture. So what happens is we enter in the region and we are fully enclosed in here. So that took all that energy. Right now, if this were region 1 where the continuous magnetic field and I kept drawing it through it, that I wouldn't induce any current, no more power at that point. So we've done the max amount of change. Like we've fully enclosed it and we've had that full change there. So that's the amount of energy. Then we enter region 2 and we do this, and then that's when the maximum change occurs. So that occurs, and then we have to pull it all the way out. Okay, so where there's changing, where the flux is changing is when we're generating current through the circuit in which we're dissipating power, right? So what we have to think about is, well, we're going to fully enclose in here, okay, and then it's going to drag it through here, and then we'll fully enclose, and then we'll fully pull out. I think it's going to stay the same. And it will stay the same because the change in flux is, ultimately the change in flux is the same. Ultimately on this one. I want to compare it to the previous set real quick to see if it was a similar situation. It was actually a different situation. It was a similar scenario being asked, but in this case, the reason there's no real change is because we're still going to get the maximum amount of change in the flux, right? So the energy is related to the time the time the flux is changing. Flux is changing. I would say because the loop is fully enclosed in region 1 and 2 for both scenarios. Like if I made region 1 very tiny, then it's different because then I'm not getting the full amount of the flux change in there, right? So the region 1 for both is seen for both scenarios. They ultimately have the same V for the same time, which implies the same power. Same power and same energy. Okay, so that would be my argument for that one. Man. Okay, the original magnetic fields are modified so that the region from here to here contains an external uniform magnetic field. B is directed in the positive Z direction. New wires connected to the resistor to form a rigid triangular loop with base length D and height D, and external force exerted to the loop. So here, this is a little bit tricky, but if we want to graph the current's related to the voltage, which is really the derivative of the flux, right? It's proportional to that. So it's D, the magnetic field, it's just the rate of change of the area. Now, the rate of the change of the area, it changes a lot in the beginning, but then it changes less and less and less and less and less and less and less. So what happens is initially you actually have a lot of current, but it's like a linear reduction. And if you're moving it across, it's a linear reduction in the area change, the flux change over time. And eventually this is like very small, so it's just going to going to be like this. D to 3D. This is going to be a straight line like that. Okay, kind of interesting because in the set 1, it was like upward because the triangle was flipped around. But yeah, that's because the area initially when I do like a little dx here, there's a lot more area than down over here. So it's going to start with more current, more voltage change in the beginning and decline to 0 by the end. And that's that question.